Okay, welcome again to Wetenskap og Demokrati, Science and Democracy. In a certain way, we will continue today the discussion of last week about what distinguishes science from other things that we humans do, what distinguishes it from things that only pretend to be science, like pseudoscience. And we'll talk this week about an idea that you can find in a recent book by the philosopher Michael Strevens. He's a philosopher at NYU in the US. And the idea is this: the innovation that makes modern science truly scientific, a certain highly strategic irrationality. So science is special because it is irrational. That is something that's initially hard to understand. I think, and that's why I have picked the excerpts from the book and a sort of popular summary of Strevens' ideas, because I do think that there is something interesting and important in his ideas. Okay, the questions then is trying to understand what this highly strategic characteristic is of modern science according to Strevens, and why think that this characteristic is something that's irrational. Now we'll start with something that Strevens starts his book with. When you look at the history of humans, depicted here, so this goes back to about 10,000 years, but we could go back even more. Humans arose about 500,000 years ago. We see animals being domesticated about 10 to 20,000 years ago. The pyramids 5,000 years ago. We see the democracy in Athens that Plato was somewhat disturbed by 2,500 years ago, the Maya in the Americas. And science comes in extremely late. So just before, that anything that resembles modern science comes in about the year 1600 or so. So science arrives really, really late in human history. There's something that seemed to be hard to discover. Okay. So one question is why? Another thing is that science does seem to be something extremely powerful. We figured out how cells work, how plants make energy out of sunlight, figured out the history of humans. We are building skyscrapers and cities without science, impossible. We are making observations about the temperature on the global temperatures on the planet. Without science, we could know anything about that. We're developing vaccines. We have developed vaccines for lots of other things. We're developing new vaccines right now. We have discovered black holes, the basic structure of the universe, the laws of nature. We've built computers and artificial intelligence systems. We have advanced medical system and so on. So all that really would be, without science, would be impossible. So science took so long to arrive, and then it's changed so much. So that really pushes this question: what characterizes this method that has that power? Distinguish it from the things that have arrived or arisen much earlier: philosophy, religion, and, well, maybe conspiracy theories, various sort of views about the universe certainly have arisen a lot earlier. And what makes science so successful? Why does it lead to this kind of technological process, medicine, construction of cities, and so on? Of course, we need to, when asking this question, make sure that there's also things that science, the negative effects of science too. So we haven't solved climate change through science, so maybe negative things too that science may have led to certain problems also. But there is certainly much progress in covering much about the world. So how was science so successful and why did it arrive so late? So these are the questions that Strevens asks in this book, The Knowledge Machine. Now let's return a little bit from last week, okay? So last week was the question, what distinguishes science from pseudoscience? And we looked at some unsuccessful attempts. That uses experiments. We've seen, well, alchemists have used experiments too. That requires proof. We hardly ever find proof in science. That it uses theories that are supported by facts. That is not really something we could make so much of a clear sense of. The method of falsification that Popper was really very interested in seems to not really work. And then we look at two ideas that seem to work a little better by Lakatos and Kitcher, that science is organized into successful research programs. Those programs make bold and surprising predictions, have internal unity, create new areas of research, and they use, if they use auxiliary assumptions, ones that are testable. That I find in Kitcher. Okay. So these are some ideas we saw last week. One way to look at Strevens' book is that he's trying to make more progress at this question. Can we say something more about what makes science stand out? So this is when we distinguish, when we look at someone that pretends to be science, we can distinguish from non-science. But how is science different from the things that philosophers do and so on? That maybe that idea of research program doesn't speak so directly about. So it's kind of asking the same questions, pushing a little bit, pushing further, and maybe asking deeper about what really makes science special. Now, in the background of the text that you read for this week is something that Strevens acknowledges, that scientists, the people who do science, are highly subjective. There isn't this grand idea that they use particular methods, they use particular, that they are, maybe more careful reasoners than others. That he doesn't believe. So Strevens thinks that scientists' decisions and beliefs are, in an important sense, subjective. So he's, in this sense, more on the side of William James than Clifford that we discussed. The evidence, also scientific evidence itself, is never conclusive enough, and it's too complex to ever force a single theory as us. So that leaves to scientists subjective standards that they need to use to really, in that complex set of evidence that there is, make up their mind about which theory they believe in. And that they do, there's a certain kind of a leap that they must take to use this evidence from the evidence to believing a theory. And so part of that leap is, when you remember William James, that they need to decide how much to weigh believing only truths of being very safe, and avoid falsehoods being very safe, believe truths. So make sure that you also have enough true beliefs. Here it's important to remember that. So in a certain way, Strevens is on the side of James here, that scientists also need to take a certain leap, just decide at some point which theory to believe. So why does he think that? Here's an example that I think brings out his ideas in a powerful way. Eddington was a physicist the early 20th century. And he was working in England, and he was interested in Einstein's new theory of relativity, in the general theory of relativity. The general theory of relativity is a theory of gravitation. So what makes bodies like the sun, or hands too, in a much, much smaller scale, what attracts them to each other, massive bodies. And it makes prediction, namely, and let's see, you displayed this here, that that massive body would bend rays of light. So that means when you, from the Earth, look at the distant stars that's behind the sun, since the sun would bend the light, the star would appear in a slightly different location. Okay. And this is, of course, normally very hard to observe because the sun is so bright, but you can observe it through a solar eclipse. And in 1919, that's when Eddington worked, he knew that there would be an eclipse of the sun, where the sun would be covered by the moon, where this bending could be observed. And so it would be a test of Einstein's theory. So there's an image here on the right-hand side of that 1919 eclipse. It's like a negative. This experiment is widely regarded as extremely successful and as a powerful proof that Einstein's theory was right. So here's from the Smithsonian Magazine. It says the total solar eclipse 100 years ago proved Einstein's general relativity. Okay, so that was 2 years ago they published that. So it's widely regarded as the kind of bold prediction of exactly the type that Lakatos talked about. Surprising prediction that proved that Einstein's radical new idea was right. Okay, but let's look a little closer. When one looks actually at the physics, then it turns out that Einstein makes a particular prediction, Einstein's theory, that in the relevant circumstances, light would bend at an angle. So how much the angle, we don't have to get in detail what exactly the angle is. The angle is a number that it predicts, and it's 1.74. Newton's theory actually also predicts that you would have a sort of bending, but the angle that it predicts is much less. It's 0.87. Okay, so now, of course, you look at the data, and what do you see? So there's a table it's from this table I picked from Strevens' book, but it's actually directly taken from Eddington's original observations of his data. So you observed various angles and took the average of that. So normal scientific procedure. And what's the average? 0.87. Let's go back to this. Newton predicts 0.87. Einstein predicts 1.74. We get the result 0.86. What? This is not Einstein's prediction. It's a direct falsification of Einstein, one might say. So wasn't this a direct falsification? Why do we still believe the general theory of relativity? Well, the thing is that Eddington argued that those measurements that led to these results that are in that table were not right. They were faulty. So one needs to then get into a little bit more detail of the relative science. These observations were not made in England because it was too bright in England, because the eclipse was visible only in South America. So they brought telescopes from England to Brazil, and there you see how they are laid out there. This was in a rainforest because that's a good place to observe. There was no light from a city and so on close by. The telescope was laid flat like this because that provided a good angle to observe the sunlight. What Eddington argued is that these facts that this was done in this hot rainforest with high humidity, that they were flat, not mounted. This, he argued, explained why the data were distorted. The photographic images from which these numbers are calculated were created by a sort of bending of the lens in the telescope, he argued, and therefore should not be taken seriously. So why do we believe the Einstein theory then? It's because there was also a different set of data. So he had two telescopes that did whose data did correspond to Einstein's predictions, but those were thrown out. Now, was he right to do that? Is that problematic? Well, not really, arguably. That is the common situation. That's why I want Strevens use that to illustrate the necessary subjectivity of science. A theory by itself doesn't make any specific predictions. It needs auxiliary assumptions. And they can always be protected. So that's what Lakatos called the protective belt of a theory. And here, so, the theory, Einstein's theory predicts that this is the angle given that the telescope works, for example. And any scientist who looks at some observation needs to make up his own mind or her mind, given this complex and messy situation where you have a theory, you have various auxiliary assumptions about various, sometimes very specific things about how a telescope reacts to heat and so on. And in that messy interpretation, in that messy making up your mind, given all these complex things, biases, subjective experience, background beliefs, assumptions, and so on, will come in. Now, part of these background assumptions are scientific in a sense. We know that Eddington was in a certain sense right. There was reason to think that the heat and humidity of the rainforest would affect the mirrors in the telescope. But part of the background is also political. We know, for example, that Eddington, this is some of the Strevens emphasizes, Eddington very much wanted Einstein to be correct. So sort of you'll see them hanging out. They're a friendly bunch, but not only that, Eddington thought that the theory was extremely beautiful, was mathematically extremely elegant, and he thought that it's got to be right. And he, as a pacifist like Einstein, so this is 1919, this is just after the First World War, wanted in this difficult post-war period to show that science is something that can transcend post-war boundaries, and that he, as an Englishman, can work on a theory discovered by a German or someone working in Germany and Switzerland. Well, I think at that point Einstein was working in Germany. That it can transcend these boundaries. So these values did drive him as a scientist to test this in the first place and to try to confirm Einstein. So he was very much trying that. So he made that leap to believe Einstein, partly on the basis of scientific values, but arguably partly also on the basis of these more political values. And we'll talk more about this, the role of values in science next week. Now, why then? Why didn't science make these subjective these leaps and rely on subjective assumptions? There's a certain sense it's a logical point. They have to. Before you test any theory, you must already assign some likelihood to various propositions before you can start testing. You have to assume. For example, I think I spoke about this last week. You must assume it if you're, for example, someone when you're 15 and doing your first scientific experiment, you assign some likelihood. It's very likely that you're making a mistake in running this experiment. And this will do with everything. So before you start testing anything, you have already assigned some probabilities, some chances, some likelihood that various things are true. And you have to start like that because you have no other chance. Before you start testing, you already have to start with something, because you have to use some experimental methods. You have to use some instruments and so on. And that assigning because it happens as well before you start any observations, has to be subjective. It can't be driven exactly. It can't be followed just from the evidence. So there isn't going to be a hard standard for how to start the process of science. Okay, so there will always be some subjectivity in science. But now note, the subjectivity of scientists' decision to believe one theory or another, I've just talked about, as in Eddington's case. That's not what Strevens means when he talks about the irrationality of science. That's not what it is. Indeed, he thinks that the method of science is what makes it transcend the subjectivity of science. So according to Strevens, there is a certain method that science uses that enables it to transcend what individual scientists do, to explain, and how science can be a project that can go beyond the subjective biases of particular scientists. So that will be next part of the lecture.